Welcome to Design of Steel Structure. So in our past video lecture, we have covered the theoretical background of this built-up column. So in this video lecture, we will cover this numerical problem from built-up column. So as you can see the numerical on your screen. So I will suggest you to understand this question first before you attempt to solve this question. So the question is design a built-up column 10-meter high or 10-meter long to carry factored axial load of 1080 kilonewton. The column is restrained in position but not in direction at both the ends. So at both the ends, the same end condition are provided. Provide single lacing system with bolted connections. Assume steel of grade Fe410 and bolt of grade F4.6. And there are four questions. That is number one, design the column with two channels placed back to back. So they have specified the section. That means we have to use channel section for this question. Number B, design the column with two channels placed toe to toe. So the orientation is specified in this option A and B. And in number C, which of the two system is economical? And number D, design the lacing system with side welded connection for channels back to back. Okay, so we'll try to solve one by one. So first is, this is very important, that is question number A, design the column with two channels placed back to back. Okay, so to solve this numerical, we will go with the design steps which are discussed in my previous video lecture. So the first step, as it said, you have to assume some trial value of design compressive stress for Fe 250 MPa. Okay, so it should be around 125 to 175 MPa. Okay, so let us see. So as you can see, the steel grade of Fe410 is mentioned. That means yield strength will be 250 MPa and bolt will be 4.6. So you know the other specification from this 4.6 grade bolt you can find. Okay, so now these points should be mentioned. Okay, and then as you can see the question, this load is 1080 kilonewton. So this load is kilonewton, so that is in, they have converted in newton, and then overall length it is 10 meter. Okay, so now effective length should be found, because effective, depending on the effective length you have to find the slenderness ratio. So effective length is dependent on the end condition. So in the second line of the question, the column is restrained in position but not in direction. That means what? Restrain in position, that means translation is restrained but not in directions. That means it can rotate. So that means the ideal support or end is the hinge. So for both the end hinged, you can find the effective length factor from the IS 800. So if you go to IS 800 2007 in table number 11 in page number 45, you can see here, that is translation is restrained, rotation is free, it is allowed to rotate. Translation is restrained, rotation is free, so it is 1.0 into L. So the effective length factor will be 1. Okay, now here the effective length is equal to 1 into 10 in meter. So let the design axial compressive stress for the column is 150. So you have to choose in between 125 and 175. So they have chosen 150 MPa. Okay, so this load should be carried. Okay, and the design compressive stress, which is assumed it is 150. So you can find the required area, cross-sectional area, to carry this amount of load. Okay, so that load by this allowable axial compressive stress which is assumed, so it is 1080 into 10 to the power 3, this load by 150, so it is coming 7200 millimeter square. So see, in the question number A, you have to select two channels placed back to back. Okay, like this. Okay, two channels back to back. So the area of this two channel cross section is 7200 millimeter square. Okay, so area for one section will be 3600. So we have to go to this steel table to choose a section, channel section, where the area will be at least this 3600 millimeter square. It should not be less than this 3600 millimeter square. Okay, so if you go to steel table, they have chosen ISMC 250. So let us go to the steel table. This is the channel section, and ISMC 2, they have chosen ISMC 250 at the rate of 298.2 Newton per millimeter. ISMC 250. So this section, if you concentrate, so you can see this section they have chosen. Okay, so this 298.2, this is in weight per meter length in Newton. So they have chosen this section. So first thing is you have to verify whether this section will be sufficient or not. Okay, so how can you verify this case, that is whether it will be sufficient or not? So for that you have to find the slenderness ratio of the built up column, and you have to use the table 9 to find the actual design compressive strength of the column, and you have to multiply this actual design compressive strength with the area provided. Okay, so that will give you the actual load carrying capacity for this ISMC 250. Now see, here they have just put these values from the steel table. Area is this, RZ, RY is this, TF, thickness of flange is given. So area provided is equal to two sections, that way it is 2. So in the design of built-up columns with two sections, the sections are so spaced that the least radius of gyration of the built-up column, built-up section, becomes as large a value as possible. Okay, so this thing has been discussed in the design steps in the last video lectures. Okay, you know all these concepts. Okay, so I will not discuss about this concept in this numerical. Everything is discussed in previously. So here you can see effective length is equal to 1 into 10 meter. So this is this maximum radius of gyration, that is r into r equal to rz. So maximum one is selected because we have to place these two channel section in such a way that this rz will be the minimum one, that will be governing minimum one, and we have to increase this ry by placing these two channel section in a particular spacing. Okay, so that in that case rz would be the minimum one. Okay, so that rz, minimum radius of gyration, is r is equal to rz 99.4 millimeter. Okay, so L by R is equal to 100.6036, and effective slenderness ratio, that is for lacing column, you have to increase by 5%. Okay, which have been discussed previously. Okay, so 1.05 into L by R, so it is 105.63. so we have to again check it should be within the limit, uh, permissible limit. So for compression member, the permissible limit is 180. It is also mentioned in the IS 800 2007. Okay, so where it is mentioned, it is mentioned here in table number 3. You can see the member carrying compressive load resulting from dead load and imposed load, it is 180. So in our case the slenderness ratio is becoming 105.63. So for this slenderness ratio and this yield stress, okay, you have to find the design compressive stress. Okay, so you know this, how can you find this design compressive stress? Okay, so as this is channel section, so we have to select these let us go to the compression member part. So as this is the channel section, so So for channel section, you see this is the channel section here. So the buckling class will be C. Buckling class will be C. So you have to use table number 9C to find out the design compressive strength for this channel section. Okay, so you can use this table number 9C. So this C. So on this table you have to find, go to this KL by R, and on the horizontal axis that is yield stress. So you have to select these 250. Okay, and you have to select this KL by R. In our case it is 105 point something. Okay, 105.63. So you have to find these if this design compressive stress for this slenderness ratio and for this yield stress. You know how to find this, so I will not discuss about this point. So they have got FCD is equal to 100.02. So if you know this design compressive strength, you can find the actual design compressive load carrying capacity for this section which is chosen here. So PD is equal to FCD into AE. So this is FCD and this is the actual area provided, not the area which is required, because this is required and we have provided some more area, no? So you have to multiply this area, actual area provided, so you can find this load carrying capacity in kilonewton. So as you can see, it is less than this 1080 kilonewton, so it is not sufficient. So you have to try the next higher section for this column. So next higher section, as you can see in the table, it is ISMC 300 and it is at the rate of 351.2 Newton per meter. So they have chosen this. Again, they have mentioned all the specifications. Okay, an area for this section is 2 into 4564. This is for one area. So for two section, this is the total area. Okay, so minimum radius of gyration for this case will be the 118.1. So this is okay. So L by R is equal to this thing, you know, so 84.67. So effective slenderness ratio will be 1.05 into 84.674. So you can see it is this. Again you have to check the design compressive strength for this KL by R and FY, and using this table number 9C. Okay, so this thing you can do it. So FCD is becoming 122.65. Okay, so next is design compressive strength. So it is FCD is equal PD is equal to FCD into AE. So this is becoming more than this load which is coming on the column. So we can select this column now, as the load carrying capacity of this column is more than the actual load which is coming on the structure or the column. Now the next step is, let us go to the design steps. So as you can see, we have found this area, and now we have to place these two channel section, and we have to find the spacing for this placement. Okay, so we have to place these two channel section in such a way that this ry becomes equal to, at least equal to rz. That means iy is will be equal to at least iz. So iz is equal to, so there is two channel section, that's why it is 2. So this equation has been discussed previously. So 2 into iz equal to 2 into iy plus this, because see here is two sections. Okay, and cg was here for the one section, cg was here for the another section about this y-axis. Now z-axis is not changing for the two channel sections, only the cg about this axis is changing. Okay, that means y-axis, cg line of the y-axis is changing, so you have to shift the axis. That means you have to find the moment of inertia about this new axis. That means you have to apply the parallel axis theorem here. Okay, so this thing is applied here. So 2 into iy plus a into the h square. So h is equal to s by 2. So the spacing between these two channels is s. So the spacing between these two axes is equal to s by 2 plus cyy. Okay, here you can see, so this is the new axis and this is the cyy. Okay, so the distance is equal to s by 2, this is s by 2 and this is cyy. Okay, so that thing is utilized here. So they have got 183.10. Then after getting this spacing, what is our target? So let us go to the design steps again. So here you can see we have to design the lacing, means in which angle we should place this lacing. So it is suggested that we have to place this lacing at an angle of 45 degree. Okay, and after placing this we have to check these conditions. Point number 9, that means you have to find this a1 by ry, and yeah, there are some conditions, you have to verify these conditions. Okay, so let us go to the numerical. So spacing of this lacing bar, so spacing of the lacing bar will be, so spacing, you know what is the spacing of the lacing bar, so that is mentioned here. So spacing will be this spacing, okay, from this bolt to this bolt. Okay, so this a1 should be found. So a1 can be found by making a triangle here, okay, like this will be one triangle and this will be another triangle. Now you know the procedure which is described in the previous video lecture, so go through that. Okay, now this a1 is equal to 2 into s plus g into cot theta. So it is 567 millimeter, so this spacing is 567 millimeter. Okay, so a1 by, so let us go to this design steps. So read this a1 by ry is not greater than 50, so it should not be greater than 50 or 0.7 times the slenderness ratio of the member as a whole. So you have to check this condition. So a1 by ry, so ry you see that is 26.1. Okay, so it will not be rz, be careful about at this point. Okay, so you have to use the ry, original ry. Okay, so this a1 by ry is equal to 21.724, that is less than 50, that means hence okay. a1 by ry should be also less than 0.7 times the overall slenderness ratio. So overall slenderness ratio was 88 point, where uh, here you can see, here it is 88.90. Okay, so 0.7 into 88.90, so it is 62.23. so this 21.724 is less than 62.23, so which is all right. Okay, so maximum shear, now we have to design this lacing bar. Okay, so as it is suggested that 2.5% of the total compressive load will be acting on from the lateral side, so the vt is equal to 2.5% into the total compressive load which is coming from the vertical direction, so it is 27,000 newton. So transverse shear in each panel, so here you can see there is one panel and there is another panel. Okay, so the total load is coming, that is 2700 newton, and it will be shared equally on these two panels. So on this panel half, on this panel other half. So transverse shear in each panel, that is 13500 newton, right? So compressive force in the lacing bar, that was discussed early. So uh, here from this figure you can see the compressive force on the lacing, that is Vt by n cosec theta. Okay, so it is just discussed early, you just go through that. So Vt by n cosec theta, so you know Vt by n, that is 13500, so you know the angle theta. So it is 19091 Newton. So 19.091, so 19.09 kilonewton. So we have to provide required specification for this lacing bar, so that this compressive load, that is 19.09 kilonewton load, will be carried by this lacing bar very easily. Okay, so in case of lacing bar design, what are the steps? So steps are, you see the steps with, you can see the minimum width should not be less than 3 times the nominal diameter of the end connector, that means the bolt. So it should be at least 3 times the diameter. So if you choose 16 mm diameter bolt, okay, so the minimum width should be 48 millimeters. So in rounding up, it will be 50 millimeter wide. Okay, so the thickness will be as per this criteria. So for single lacing system, so in our case it is single lacing system, so it should not be less than 1 by 40 of its effective length. So effective length, you can see what is effective length. So this length is the effective length. Okay, total from this point to this point, this length is the effective length. So how can you find the effective length? That is also discussed in the previous video lecture. Just go through that. And you have to find the thickness here. So thickness will be 1 by 40 into length of the flat between the inner end bolts, that is 183 plus g into cosec theta. So it is 10.02. So in this is the minimum one, so you have to increase this one. Okay, just they have increased by 2 millimeter around, so it is 12 millimeter thickness. Okay, so provide a flat section 50 millimeter wide, Indian standard flat, 12 millimeter thickness. Okay, now you have to check the strength of this lacing. Okay, so to check the strength, you have to find the slenderness ratio. To find the slenderness ratio, you should know the minimum radius of gyration. So the minimum radius of gyration as suggested by these guidelines are t by root 12. Okay, so t have been found 12 millimeters, so 12 by root under 12, so 3.464 is the minimum radius of gyration. So L by R, you can see, so L is equal to, L will be the effective length of the flat between the inner bolts, so that is equal to 183 plus 183.5 plus 50 plus 50. So that is the length of this from this point to this point. Okay, so that is L. So L by R is equal to 11.5.72. So it is less than 145 as suggested by the design steps. Okay, or IS 800 2007. Okay, so you have to find the design compressive strength for this flat bar, for this slenderness ratio. Okay, and for this yield stress, and you have to use the buckling class C. Why buckling class C? If you go to the table, these tables, you see this is the cross section of the flat, so you have to use the buckling class C. Okay, so uh, again you have to go to the table number 9C of the IS 800 to find the FCD for this L by R and this yield stress. So you will be getting 88.365 Newton per millimeter square. So the design compressive strength of the lacing bar is equal to AE into FCD. So area of the cross section. So area of cross section, that means here they have chosen 12 millimeter thickness, and uh, this width is equal to how much? 50 millimeter. So area will be 50 into 12. Okay, into this design compressive strength. So it is 53.02. That is more than this 19.09 kilonewton, which is coming as a compressive load in the lacing bar. So hence it is sufficient. If we provide this lacing bar, that will be sufficient. Okay, now another thing is that if there is some reversal of load, that means by due to the wind load and earthquake load, you have to the member or the lacing bar will be subjected to some tensile force. Okay, there may be this case. Okay, so you have to um, ensure the, if there is some tensile force, it will not fail. So the design tensile strength of the flat can be found by this. So this thing you have solved in this first chapter, in the tension member chapter. So 0.9 into b into minus dh, that means the net section rupture. Okay, this thing you have solved in the first chapter, you can go through that. Okay, and this is gross section yielding, net section rupture and gross section yielding. So here it is 113 and it is 136, so both are more than this 19.09, so hence it is safe. Now this connection, now if we use this what this type of connection, okay, like one bolt is connecting these two lacing bar, then force on the lacing bar is how much? It is 2 into Vt by n cot theta. Okay, if it is if the one lacing bar is connected by one bolt, then it is Vt by n cosec theta. So in that case, they have connected this like this. Okay, so 2 v into Vt by n cot theta will be used. Okay, now here in the design of connection, you have to find the design strength of the bolt as well as the force which is coming on that bolt. Okay, so they initially they have found this strength of the bolt. Okay, so as two lacing bar is connected by one bolt, so it will be subjected to double shear. So you know this, how to find out this strength of the bolt in double shear. Okay, this thing is practiced in your class. Now strength of bolt in bearing, this thing is also known to you. Okay, so out of these two strength, lesser one will be the governing strength, so 58.01 kilonewton. So force on the bolt on the lacing, from the lacing plat, it is 2 into Vt by n cot theta, that is mentioned in the here design step 17. Okay, or in IS 800 2007. Okay, so it is 27 kilonewton. So 27 kilonewton load is coming on the bolt and the strength is 58.01. You can see, so only one bolt will be sufficient. So number of bolts required, it is equal to load which is coming by strength of one bolt, so it is 0.465. so you have to provide at least one bolt because you cannot provide a half bolt. Okay, now if you provide this type of connection, then the strength of the bolt will be subjected to single shear. So they have just use this previous data here to find out the shear strength. So 29 and strength of bolt in bearing, so that is this. So the lesser one will be the governing one, so it is 29.09, 29.0 kilonewton. So force on bolt from the flat is Vt by n cosec theta. So that means you can see the design step 17, so it is 19.09 kilonewton again. So the number of bolts required, so 19.09. So you see the strength is 29 and the force is coming 19, so only one bolt will be sufficient. Okay, so you have to design the tie plate. So at the end you have to provide the tie, where this tie plate, okay, we can see this tie plate. So in the design of tie plate, in our last video lecture we have discussed this. So you have to find the effective depth. Effective depth is equal to S dash plus 2 CYY. So S dash, that means spacing of these two channel section 183.5 plus 2 into CYY. So this thing you can go through this, go to this steel table. Okay, so this thing you have mentioned in this specification of this section. So CYY, this is this. Okay, so this thing is used here. So this effective length is 230.7 and it is more than 2 into 90. So it is mentioned in IS 800. Here you can see uh, in this tie plate. Okay, in pattern design, so in page number 51, you can see the intermediate. See, in no case shall the effective length of any pattern be less than twice the width of the one member. Okay, so in the plane of batten, so width of the member is this BF, so it should be more than this 2 into BF. Okay, this is also ensured. overall depth of the typelet it is, so this effective depth plus 2 into what it is edge distance. So edge distance is how much? So for 16 millimeter diameter bolt it is 1.5 into hole diameter, so it is 27. So it is minimum 27. So they have provided 30 millimeters, so it is 290.7. So overall depth they have chosen 300 millimeter in the round up figure. Okay, now length of the typelet. So typelet is equal to this. So length, what is length? So length is basically this length from this point to this point, from this edge to this edge to this edge. Okay, so it will be s, so this spacing is s, and this is how much? bf, right? So the spacing or the length of the typelet will be 183 spacing into 2 into 90, that is 363.5. So in the next round up figure is 364 millimeter. Okay, so thickness of typelet is already mentioned. Okay, here thickness is equal to, it should not be less than 1 by 50 of the s dash plus 2g. So you know this s dash and 2g, so just use this formula. S dash is 3.5 and g is 50, so 2 into g, so 1 by 50. So it is it should be at least 5.67, or it should be more than this 5.67. So you can provide 6 millimeter thick typelet. Okay, so the specification of typelet is 364 into 300 into 6 millimeter, and connect it to the channels with 16 millimeter diameter bolt. So these bolts will be 16 millimeter. This bolt is also 16 millimeter. So this is total numerical. So you have to, in this numerical you have to just find these channel sections, find the spacing, find the property of the lacing, and also the property of the batten. Okay, so I will suggest you to just go through the previous theory lectures on the built-up column and also this numerical. Then only you will understand this total numerical, if you understand the theory part. Okay, so in our next video lecture we will go to the column based design.